I am thrilled. I'm Lydia Kavraki. I'm the director of the Ken Kennedy Institute, and I'm just thrilled today to introduce to you our speaker, Dr. Wolfram Burgard. Wolfram Burgard is the VP for Automated Driving Technology at the Toyota Research Institute in Los Altos. And he is currently on leave from his professorship for autonomous intelligent systems at the University of Freiburg in Germany. His interests are broadly in AI and robotics. I asked for his bio, and the bio says he has made substantial contributions to several relevant problems, including state estimation, navigation, localization, SLAM, and mobile manipulation. I want to tell you that he is the person, okay, who has really introduced the Monte Carlo localization, a probabilistic approach to mobile robot localization that is based on particle filters. Has been a major contribution that really changed the field of robotics. If you don't know where a robot is, there's very few things you can do with this robot. And also he and his group made very substantial contributions to simultaneous localization and planning, what we call the SLAM problem, which is to determine the map of the environment and the position of the robot at this environment at the same time. So his CV, I mean, his bio is really very, very modest. For his work, he has won the AAAI Classic Paper Award not once, but twice. The second time, I believe, was for Monte Carlo localization. And the first time was for an interactive robot for museums. He is a co-author of two very widely used textbooks in robotics. One is Probabilistic Robotics, and the other is Principles of Motion, of Robot Motion Theory, Algorithms, and Implementation. For his work, Wolfram Burgard has received the Gottfried Leibniz Prize, which is the most prestigious German research award, and an advanced grants from the European Research Council. He's a fellow of AAAI, the European AI Association, and IEEE, and he's actually the past president of the IEEE Robotics and Automation Society. The University of Freiburg was elected as one of the 17 early centers for excellence in machine learning in Europe, and he will be heading this group. So without further ado, I would like to welcome our speaker.
Thank you. Thank you, thank you. It's a pleasure to be here, and I'm a bit nervous about being able to meet your expectations after that introduction, but I will try to do my best. So today I'm going to talk a little bit about what we are doing at TRI, and how I got there, and how we actually came to an agreement how this technology that we have been working on in the past actually applies to self-driving cars, and how we are going to approach solving that problem of self-driving cars. And the cornerstones of that presentation are basically probabilistic approaches on the one side, and on the other side, machine learning technology, which are, from my perspective, the future technologies for developing all kinds of robotics applications, and including self-driving cars. And so that is how this title actually came into existence. So we're going to talk a little bit about the background, probabilistic approaches, then I will go over to what we are doing at TRI, and right now maybe a little bit abstract, Guardian and Chauffeur, our current products and strategies that we are working on. Then I will talk about challenges, then what we believe is the data advantage that TRI in combination with Toyota is having, and then we'll come to an end with a little summary. So let's go to the background, and I have to warn you up front, I was told by Lydia that there's also people from different departments, that it should be more on the lightweight side, this talk. You should be aware of the fact that robotics does not work without math. Right, so there will be a few equations in that presentation, but I will try my best to actually explain how they actually work. So don't run away as soon as you see an equation. So I will try to explain it in a few minutes after it appeared on the screen. So what we are actually interested in, and that is independent of as to whether you're building self-driving cars or just robots that perform delivery tasks in factory floors, We want to build agents that are able to actually understand the world, reason about what their tasks are and how they can achieve them, and basically also then execute actions to modify and change the world. It's a relative simplistic representation of that what we are aiming at, but in the end, basically the key lies in that model over here that the agent needs to have in order to make all these inferences, understanding the world and figuring out what the next best action should be. And in this talk is basically about how can we generate models that help robots executing their tasks. So the first thing that you need to be aware of when you're faced with a real robot in the real world is that unfortunately there's no such thing as a perfect sensor. Right? Independently of what sensor you take, every sensor comes with uncertainty and potential errors. And here's one example. It's actually data that is more than 20 years old, but it's an interesting application. What you see here is an environment with a red line, which is basically the trajectory of a robot that was teleoperated or manually controlled in that environment and along that path. And how robots work is basically how robots measure their movements is basically with so-called wheel encoders that are tiny little disks attached to their axis, and that actually have black and white stripes, and they basically count the number of black-white transitions in order to figure out by what angle a wheel has turned. And if you think about a car, for example, and you measure it, that's basically what your automatic brake system also does is when it doesn't, when the wheels don't rotate anymore, it releases the brake to make them rotate again. And you can use the very same data to actually do a little bit of geometry, equations, and accumulate those over time to figure out how much the robot has moved. And therefore that all you need is basically the radius of the wheels and the distance of the wheels. And once you have those, you can actually measure how much the robot has moved. And the unfortunate, that is not very accurate because we don't live in a perfect world, and all the assumptions and models that we are having are all inaccurate. So if you do this, then typically what you obtain is a trajectory like this one over here, which means that you cannot entirely trust your sensors. Right? Same as with distance sensors. You might now say, oh, but why can't I use a camera or a LiDAR or whatsoever sensor in order to figure out where the robot actually is? You can actually, that's a valuable approach, and this is one example of 24 ultrasound measurements recorded by the very same robot at that location down there in the center of that map on the left-hand side. Right, so, and what you can see from this is that these measurements more or less fit to that map, apart from the two on the right-hand side that apparently go through the wall, which is something like typically observed with ultrasounds. It's called a specular reflection. And there's also two that end in the middle of nowhere, like those one over here, right, which are actually reflected by the student holding the joystick and following the robot, which means that whenever there's something dynamic in the environment, measurements don't fit. So you might now argue, okay, you can use that information to figure out where the robot is, which is not entirely true since this environment is somehow ambiguous. So that entire space over here, which is that place over here, is actually symmetric. If you take just one observation, the robot doesn't know as to whether it's facing north or south, right, because of symmetry. Right, so the only solution to overcome that problem is integrate measurements over time. Right? How do you do this? And the best way for doing this, and this is the argument, is going to a probabilistic approach and basically have probabilistic reasoning for doing so. You can also take more accurate sensors in a different environment here. These are LiDARs or laser rangefinders, super accurate devices, but and you can see these red ones over here, the ones depicted in red, more or less correspond to the map. Obstacles are depicted in black. And the other ones, the blue ones, are kind of like random. And this is actually data recorded with that museum tour guide robot that Lydia mentioned. And that robot was operating in a dynamic environment, surrounded by people, guiding people through a museum, those people are not contained in the map. And because of that, the majority of these measurements were actually not corresponding to what the robot expected. And how can we make a robot being able to deal with that? And the answer to that, as mentioned, is probabilistic approaches, and that basically led to that notion of probabilistic robotics. And here is equation number 1. Right? If you don't want to see it, close your eyes now. Right? So it's basically this equation over here, which is called the recursive Bayes filter. It's basically nothing else but a probabilistic approach for estimating or for representing the belief of the robot where it is in the environment. It's kind of like a probability distribution about all places where the robot actually could be, and it assigns a value to every of these places. And the two components that go in there are briefly the so-called prediction model, that is P of x given u and x prime, which basically means the probability that I end up in x given I was in x prime before and executed action u. That basically is nothing else but a probabilistic representation of that error model for the odometry. So basically it tells, if my odometry tells me I have moved, or the wheel encoders tell me I've moved 1 meter forward, if I create a statistics and let the robot move or give it the command to move 1 meter forward, where does the robot actually end up? You calculate the statistics about this, and this is nothing else but this statistics. Relatively easy to accumulate. The other important component is this one over here. It's the likelihood of measuring Z, of getting a LiDAR distance or distance from a LiDAR, given the robot is at a specific location. And both terms are used in that equation to actually figure out where the robot is. And the same holds similar, when it comes to action, you can also go for a probabilistic approach, which is from the domain of reinforcement learning, where you basically calculate a policy that interestingly calculates similar terms, and you find the same transition model that you have here also there. So that is basically the mathematical foundations of probabilistic robotics. Key challenges there are basically dealing with the high dimensionality of these underlying spaces. So let's talk about how this actually works in practice, and I promise I'll tell you, give you an intuition for every equation. Let's talk about the first one, the state estimation problem, how to actually calculate a probabilistic belief. And for that, we're going to talk about a robot that lives in a one-dimensional world. So imagine that there's a corridor living in one of your corridors here, in which the robot can actually only move forward or backward. It's kind of like a robot on rails. But still, that robot might face the problem of where am I in that corridor relative to the beginning or the end of the corridor. So it's also the very same problem, but just in one dimension. If you switch that robot on, robot has no idea where it is, then you have a so-called uniform distribution. Every place has the very same likelihood, which is that function over here. It's a uniform distribution over all states, potential states. So now let's assume that the robot has some sensor that tells it that there's a door in front of it. And because its corridor has 3 doors, and let's assume that sensor fires, what happens is that the probability for being in front of one of the doors actually increases. And you end up with a distribution that has 3 peaks, 1 for every door. Now let's assume the robot starts moving forward, and what we saw from that graph with the odometry, basically that increases uncertainty because these measurements or these devices are not accurate, movements are not deterministic, so the robot actually loses information while moving forward. Which means, and mathematically, if we go back to that equation, over here, that is the right-hand side part, that's like this integral over here. You basically calculate an integral over all potential prior positions and then multiply that probability with the state transition probability. And with that you obtain actually the probability of ending up in a specific place given all other places and the probability of having gotten from that prior place to the place under question. So and that is basically that operation over here, that integral is basically the transition from here to here, where you kind of like shift this distribution and smooth it, so to say, which is the loss of information that comes with it. Left-hand side part is we basically multiply that the outcome of that integral with the observation likelihood, like how likely is the observation given my current state. Turns out that this observation likelihood is exactly this that we have seen over here, because here's a constant, and we multiply that by that function, so it's basically proportional to that function. Which means that if we multiply that integral over here with that equation, or with this term on the left-hand side, all we do is we multiply that function over here with that function over there, which gives us exactly that function. Now we have 5 peaks. One is consistent with 2 observations, and one is consistent with, the other 4 are consistent with just 1 observation. And where there's no peak, that is consistent with none of the observations. Right? And the hope is now that over time, as the robot proceeds and observes doors while moving back and forth in that corridor, maybe doing some delivery tasks or transportation tasks, it actually figures out exactly where it is in that corridor. All right, so this is basically the mathematical background. The question is, how can you actually implement this in a way that it becomes efficient even on small-scale computers? And the key idea is that what Lydia mentioned in the introduction, or one solution for doing this is a so-called particle filter. It has nothing to do with a filter for dust or so. It is just an approach where you basically represent that belief, that function, by a set of hypotheses which are called particles. We will see this in a few seconds. And or let's move forward from that to that, and then I'll explain this over here. So basically, what you see in this figure is in the bottom line under the corridor is a set of randomly drawn hypotheses. You just take your random number generator, and then you project those numbers into that corridor, and then what you obtain is that distribution of hypotheses or particles. Basically, all these tiny little towers over here. You could also do like evenly spaced sampling. It doesn't actually matter in that case. So that is the representation of a particle filter, basically a set of hypotheses. So what we do now is, like, once we obtain an observation, that what we do is we give these hypotheses a weight, which means that we increase the size of these towers proportional to the observation likelihood here. Same function as we saw before, and that what we obtain is towers of different heights. And now we apply a very interesting process, which is kind of like a survival of the fittest scheme. What we do is we consider this as a deck of cards where we multiply every card according to the height of that tower. Which means if we draw from this card with replacement, so we put it back into this card, we draw cards that come from towers with a large height, or tall towers, more often than the towers that are tiny. So which means that particles or hypotheses with a high likelihood that correspond to high likely places replicate more often. And we combine this with the motion, so we at the same time we let these particles pass through that so-called motion model over here and guess a final outcome of that movement. And by doing so, what we obtain is basically a new set of hypotheses. That's basically the idea of the particle filter. And what you can see now is an implementation of that using a robot in a real-world environment. So this is a map of, I think, the Bonn Computer Science Robotics Institute, where actually we collected this data. It's a relatively old data set as well. But here you can see a localization carried out with 24 ultrasound sensors. And what you can see is these red dots. So the grayish is the outline. The red dots are 10,000 particles or hypotheses. We don't show orientation. In robotics, for robots living on a plane, it is x, y, right? The position plus the heading. And we only show the position here. So the orientation is not encoded in the visualization. And what you also see are these measurements. And like, when you more carefully look at it, it almost fits to that place. So it turns out that the hypothesis that is underneath that visualized robot over there actually has the highest observation likelihood. Actually, the robot was somewhere over there with that beam going through that doorway here. But turns out that probably that particle or the hypothesis that is down there doesn't have the right orientation. So that we don't know. I didn't do an in-depth analysis of that, but it's probably the cause why it the robot is not, like the most likely particle is not over there. But these particle filters are actually robust to false estimates, and they have the ability to cope with uncertainty and also with noise in the measurements and also false estimates in the very beginning. So what I'm going to do is I will let this video run. The black arrow shows approximately the trajectory of the vehicle. What you will see is at the very beginning is that the robot actually doesn't know, because some of these measurements, like this one over here, actually goes through doorways. The robot figures out that where it must be relative to the doorways, but it doesn't know in front of which doorway it actually started. So you will see multiple clusters in front of doorways. And as soon as it gets closer to the end of the corridor, like the robot will figure out that there's something at the end of that corridor, and it must be, and that way, like hypotheses that are at the right spot relative to the end of the corridor get a higher likelihood and get replicated more often. So these clusters concentrate at the same spot relative to the corridor. This corridor has the property that it is symmetric, so the robot actually doesn't know as to whether it's facing west or east, and that can only be resolved by moving into one of these two rooms, right? So by moving into this room, right, it can figure out that this looks different from that one down here, right? Because of its measurement correspond to more to that room on the north, and it actually at that point in time it can entirely disambiguate where it is. So I let this video run, and you can see how these clusters emerge. At the very beginning, it gets the wrong orientation, right? But there's also now there's a right one, but this is just by chance, right? It could be that by pointing with one beam into the room, there's kind of like a higher likelihood for that orientation, but it is extremely uncertain. As you can see, we have two clusters, and as soon as the robot enters that room, even with these noisy sensors that don't fit, where the measurements don't correspond to the tables, because they sometimes go underneath it or hit items on the surface of the table, right? So we get rid of the ambiguity there. And here at the very end, it even bifurcates again because the robot doesn't know as to whether it made an orientational error there, which is also kind of interesting. Right? So that is the solution of that equation to the localization problem, and which actually is one of the foundations for self-driving cars. Many self-driving cars use exactly that algorithm to figure out where the vehicle is on the road. But you can even take this to another dimension and look at a different and very, very popular problem in robotics, which is the so-called SLAM problem. SLAM stands for simultaneous localization and mapping. So it's kind of like the problem that you have to solve once you arrive in a city you have never been to before, right? So imagine you land in San Francisco, go to the city in order to explore it, and typically what you do is you go to the reception in the hotel and ask for a map in order to figure your way around. And now imagine they tell you that they unfortunately ran out of maps. What you then have to do is you have to actually explore San Francisco and always memorize what San Francisco looks like and where you are in San Francisco and how to get back to the hotel. So that's not really a problem anymore because we all have smartphones, but in these days before you were born and there were no smartphones, that was actually the task to solve then. And if you send a robot to Mars, right, the robot doesn't have a map of Mars, and you actually do not know what the Mars looks like, where the robot lands. So the robot actually has to find its way around and get back to the base station in order to deliver probes and so on and so forth. And that is actually the problem that the robot has to solve there. And even when you want to build robots that we've seen before, robots that use maps for localization, and how do you get the maps? And that is exactly what is behind the SLAM problem. And if you take data from a robot and just project it, distance data, and black now is wherever a measurement ended, and white is the free space, and then you just project it according to the measured path, odometry again, then you end up having getting maps like this. The question is, how can we solve this problem? It's a problem where we actually have to figure out what the world looks like and where we are in the world at the very same time. And that turns out to be a high-dimensional state estimation problem with 10,000s of dimensions. And at the end of the last century, people figured out how to do this efficiently using particle filters again. And how do you do this with a particle filter? And here's just one example. It's actually the very same equation. Nothing changes in that equation. The only difference is now that our state has not only 3 dimensions, x, y, and the orientation, but it has basically 10,000 dimensions, something like that, for a reasonably sized environment. But still, with this approach, with these particle filters, with a modification of that, you can actually solve that efficiently. And the key idea is that now each hypothesis not only contains the state of the robot, but also the map that corresponds to the trajectory taken by the robot, according to that what the particle filter actually estimates. Right? So once you know where the robot was, you can actually calculate the map in an analytical fashion and very efficiently. And it turns out if you have 3 different hypotheses about the path of the vehicle, then you also have 3 different types of maps, or 3 different maps. And obviously, like one in this case, like this one over here, is more consistent with the trajectory than this one over here. Right? So we see double walls over here. And now you can apply the survival of the fittest scheme again and realize that like for map 3, like the measurements are less consistent, less likely. So particles corresponding to that map will have a lower chance of surviving that survival of the fittest scheme. That's basically how that works. And here's a visualization of that. That is the particle filter in action for SLAM. It is the very same data set as you saw before. And now basically what we do at the very same time is trying to figure out where the robot is and what the map looks like. Unfortunately, we can only depict one map. What you see in this visualization is you see the most likely map, or the map corresponding to the most likely particle, which has the highest observation likelihood over time. And this is why this map sometimes changes in places where the robot actually not is, or it appears like being so. It's simply because we switch to a different map. So that's interesting. In the very beginning, everything bifurcates, and whenever the robot comes back to a place, then there's this so-called loop closure. The robot actually figures out where it was relative to a previously seen location, and then you basically get the fact that, or you have the effect that unlikely particles die out and the map gets more consistent. And with that, you can actually build highly accurate maps, at least for reasonable sized areas, like the Freiburg campus, and people have driven that to what's extreme efficiency, like 30 particles, and large-scale environments where you can actually have robots then navigating around even in larger spaces. So the only problem with that approach is, first of all, is the scale. It doesn't really scale to city-like maps. And then there's another problem that us as computer scientists is always striking, like things like final slight deficiencies in these maps. So for example, do you see this double wall down here? Right? So as a robotics person, when you look at that, you say, no, I don't like that. You know? And the reason for this is, when they think about how this particle filter works, it basically can correct or choose the most likely map, but it cannot do any correction retrospectively. If you have, you can only live with these particles or with the places you have put particles at. And with probability 1, they are not at the exactly right spot. And sometimes you don't see it, right? And the only solution for that, to recover from that, is using infinitely many particles, but we don't have a computer for doing this. So we actually have to live with these deficiencies, unless you go for an alternative approach, which is that what has emerged afterwards, which is so-called optimization-based techniques for solving the SLAM problem, which is basically graph-based SLAM. And the idea of graph-based SLAM is the description is relatively simple. It goes back to 100 years ago, where people from photogrammetry were actually interested in figuring out what the world looks like. And there's even books about this, measuring the world. And interestingly, at that point in time, people have applied very, very similar techniques that we use right now. At that time, they also used computers, but they were kind of more flashy, actually humans. And they subdivided problems into tinier problems and used these computers to solve these tinier problems, and then they had more capable computers who actually combined these tinier problems to solutions for more complex problems, these solutions for tiny problems. And this is kind of like a hierarchical approach for solving, for calculating maps. And when you look at how the mathematical solutions for SLAM work, then it's exactly or very, very similar to that what people have done manually in the past. So how does this work? Basically, you can this is a data set again. It's actually the KUKA production site in Augsburg, Germany, or parts of it. And you basically, when you calculate or when you take a data set again, similar as before, like laser range measurements projected according to odometry. And what SLAM then basically does is it looks at that graph, calculates the path, but also correspondences between observations. Basically, like when you look at that over here, it is basically we see that this part over here looks exactly like this over here, and then by that we introduce so-called constraints, and these constraints are nothing else. You can consider those as springs in a mass spring system, and that spring basically says, okay, I want to draw that point over here to that point over there. And then even the others, like trajectories, are nothing else but springs that basically tell you, like what odometry says, where these positions are relative to each other. And the individual nodes or measurement positions are points, or weights. And what you then do is you take the spring mass system, throw it into a bath of oil for have proper damping, and you let it relax. And usually that converges to a minimum energy configuration, which is gradient descent. And once you do that, you obtain, ideally, in the ideal case, the optimal solution. Right? So we throw away the data, throw this into the bath of oil, get the position estimates, and get out of it the correct map. Right? And here's a couple of applications of that, and the so-called sparse post adjustments, where you can actually do all kinds of interesting aspects there, basically calculating these maps on the fly as you see the robot moving around. You can also do things like, in a second, like do this in a batch form. You throw all the data at it, and it optimizes over them. And then finally, you can also do something like go wild, initialize everything with 0, 0, 0, 0, 0, and random orientation, and ideally it unfolds the correct map. And with that, you can basically calculate super large maps, and companies like mapping companies that you have typically on your smartphone do this on a country level scale. So that's actually something that really scales to huge and large maps. So that's basically the key technologies that you need for robots operating on factory floors and also self-driving cars. And that actually basically made me going into TRI and trying to apply this to actually build vehicles that prevent people from being involved in accidents. And that will, let me see, I will skip that, and that I would briefly go to that, or quickly go to that. That's what we are actually doing at TRI, and how we are going to apply, or trying to apply this for cars in the real world for actually saving lives. So TRI has been established a couple of years ago, 2016, with an initial budget of $1 billion, as distributed over 3 different places, which is the Silicon Valley, Ann Arbor, and Cambridge, and focuses on automated driving, robotics, and also advanced materials. These are the 3 research areas, and is tightly connected to different Toyota companies. So the overall goal of TRI is basically improving the human condition in 3 areas. First one is safety. It's basically driver assistance systems. We'll talk brief about this in a second. Next one is access, or actually increasing mobility of people. And the third one is robotics. Particularly countries like Japan are faced with the problem of the aging population, and how we can actually get to a world in which people can live longer and more independent when they are old. And so this is basically where the robotics part kicks in. So the automated driving is centered around the car, one system, and 2 different modes. And this is what differentiates Toyota or TRI from many other companies in the area of self-driving, like, for example, Waymo, Zoox, and even Neuro, which is basically operating here, as I heard. And what we are aiming for are basically two applications. The first one is a so-called chauffeur application that is nothing else but the level 5 automation or level 4 automation. We were trying to build a car that can, without a driver, reliably get you from A to B. You enter that car in a basically mobility as a service application where you have like transportation, taxi-like transportation with self-driving cars. Right, so where this car is fully autonomous and engaged all the time. And the second approach is the so-called Guardian, where we are interested in building advanced driver assistance systems and building the car that can never be responsible for a crash. Basically, a car that can always take over and rescue you in case you made a mistake. Right? And the idea there is that you basically have a car that monitors you and it helps you whenever it gets dangerous. And they are both tightly related, and I will briefly talk about how that works. The best one to describe this is actually Gil Pratt, who is the head of TRI, and I will briefly, for 2 minutes, leave you alone with his presentation at CES last year, basically describing the mission of TRI and particularly of the Guardian.
Please welcome CEO, Toyota Research Institute, Gil Pratt.
Good afternoon, everyone, and thank you for joining us today. And thank you to Bob Carter for that perfect lead-in to what I think you will all believe was a rather vivid opening statement. The 3-car crash that you saw actually happened just as you saw it. We know this because we were there using an array of sensors and cameras. Our engineers at Toyota Research Institute captured a robust and diverse set of data to recreate what happened that day last summer. Our Lexus test vehicle was traveling in the leftmost lane in manual mode. The autonomy was disabled, but the perception system was fully active. It was mapping and gathering data at the many tunnels and bridges in the Bay Area. And luckily, despite the severity of the crash, no one was injured. We show you this now not to wow you with technology, but because I want to take you through a question that we posed to ourselves that very day. So here's the question. Could a future Toyota Guardian have prevented or mitigated the crash that you just saw? We believe that the answer is yes. So let me talk to you a little bit about what Toyota Guardian is all about. The essence of Toyota Guardian is about amplifying rather than replacing human ability. It's like giving Dad his car keys back for a bit more time behind the wheel. Or even more importantly, it's about saving teenage lives where car crashes account for 30% of fatalities. It's about correcting for human mistakes and for human weaknesses and assisting the most vulnerable people at both ends of the age spectrum, where far too many lives are lost. Now, from the beginning, TRI has been committed to a two-track approach to automated driving, simultaneously developing Toyota Guardian while working on level 4 and level 5 self-driving systems that we call Toyota Chauffeur. Now, Chauffeur is the kind of self-driving technology that all of you hear about in the press all of the time. Specifically, it's an approach that replaces the human driver with AI, with a machine. Level 5 Chauffeur is defined as a system that's capable of driving anywhere, anytime, in any conditions, with no driver input. And that's a wonderful goal. Someday, we may achieve it. But it's really essential to not underestimate how hard a task chauffeur systems are, both technologically and also sociologically in many ways. For example, how do we train a machine about the social ballet required to navigate through an ever-changing environment, as well as, or better than, a human driver? How do we teach the systems to predict what a policeman means when they motion to you to stop at an intersection even though the light is still green? Or when a pedestrian will decide to cross the road? These are hard questions. Let's also keep in mind that it may take considerable time for society to accept the inevitable crashes, the inevitable injuries, and the inevitable fatalities that are still going to happen with chauffeur systems. Now, none of us in the automobile or IT industries are close to fully answering these questions. In the meantime, we all have a moral obligation to apply automated vehicle technology to save as many lives as possible, as soon as possible.
So with that, I will skip forward in that video. He's going to talk a little bit about technology, and we don't have time for listening at everything. It's on the web, so if you YouTube, if you want to listen, look at it in more detail. So what I'm going to do is I will forward and back to that position where it actually explains how the Guardian could have prevented that accident. So here we go.
Be stretched and challenged through continuous refinement. Our Guardian systems learn how to best navigate and react to dangerous scenarios as they unfold. For example, in the demonstration that you see here, a vehicle suddenly pops out from behind a row of parked cars too quickly for any car to simply brake in its lane. Sensing that the next lane is clear, but only for a brief window, our Guardian alerts the driver, visually and audibly, of the imminent danger, and then avoids the pop-out car by maneuvering out of the lane briefly and then quickly returning to the original lane to avoid the obstruction ahead. Now, this growing Guardian capability gives the I-80 incident that I opened with today, that vivid crash that you saw, an interesting lemons to lemonade twist. Here was an accidental corner case on a public highway. A dangerous three-car encounter that unfolded right before our eyes. From the data that we gathered, we first developed an accurate simulation, which we then translated into a learning tool for Guardian to perceive, to predict, and to plan the options that it had in a split second. We then recreated that same scenario on the test track using real vehicles and a guided soft target dummy vehicle. In this instance, Guardian's best option was to safely accelerate away from encroaching vehicles to avoid a collision. And furthermore, by accelerating out of the way, Guardian did this other thing, which was to help make space that might have prevented the other vehicles from crashing as well. In this way, we actually created a kind of an altruistic Guardian, which we think is a really neat idea.
Good. So I will briefly talk about some challenges that we are facing, and you probably also know about these autonomy challenges in there. In the interest of time, I will skip about those, and level 4 and level 5 is basically that what most of the car companies are interested in, and level 3 is kind of like that where Guardian, for example, can kick in. And but the key question that always comes up is how long is it going to take until we finally have automation in cars, and when will we have self-driving cars? And there are in fact some aggressive statements about this, and you all know this person, Elon Musk, and he said, I want to say a year ago, that we will have self-driving cars where the driver can fall asleep by driving by the end of this year. We have 10 months left, and I'm looking forward to seeing that. But there are also other opinions about this, and some are a little bit more like experience and data-driven. And one is, which is very, very interesting, is a so-called Moore's law for self-driving that Edwin Olsen, a robotics colleague of us, who's now also has been working for TRI as well, has now his own startup, has come up with also almost a year ago. So Moore's law of self-driving basically means, says that we are doubling the disengagement rate every 16 months. Right? And the disengagement rate is basically the kilometers or miles per intervention. Right? So we can actually drive twice as far after every 16 months, right? Without the safety driver having to actually intervene and rescue the car and taking over. Right? And if you extrapolate this and want to arrive at the human level performance, which is basically that line over here. So that is where we are right now, and we double that every 16 months. And doubling is still exponential. You can imagine it's still a hard time to keeping that exponential evolution over time. And the time where those two lines overlap, if you want to reach human level performance, that is then basically in 2035. Even under the aggressive assumption that we are going to double this every 16 months. Unless we have that true insight that solves all of our problems, we're probably, if we keep doing this in an incremental fashion, then it's going to be a stretch doing this by the end of this year. So the reason for this is that we are faced with all kinds of challenges, like human factors, kind of left turns, and so on and so forth, maintaining maps, because robots or cars use maps for localization and for navigation planning, and then also all kinds of problems that we are faced with, and weather conditions, and so on and so forth. So these are actually the heavy problems that we are faced with, and this is also the reason why many of these companies are in the Silicon Valley, because the weather is mostly nice over there. So what car companies typically do is they use these for level 4, level 5 automation is they use what is called HD maps, highly accurate road maps with lane markings and all kinds of directions and so on and so forth for navigation, and then figure out where the vehicle is relative to that and perform planning and on these maps and execute those. With TRI, with the ability to actually, or with the need for having that guardian that is able to operate even when we are not at the level of level 4, level 5, we need to go take a different approach and basically become more sensor driven and extracting more out of our sensor data in order to figure out what the best action in the current situation might be. And this is where we are actually utilizing live perception of the vehicle and trying to develop the automation or automated driving capabilities based on live perception. So which means that we basically use the guardian in order to reach that chauffeur where we are actually needing HD maps, which are hard to generate for the entire world without an enormous effort. So this is why people are also developing right now level 4 automation, which is basically a geofenced version of level 5. It works just in restricted places, and the reason for this is that acquiring those maps is actually difficult. Right, and the solution for doing this is basically utilizing data and utilizing machine learning capabilities to actually make these inferences about the semantics. And together with these probabilistic approaches for calculating maps. So basically what you see in these tiny little windows on the left is a semantic interpretation of the vision data. And once you can extract lane markings, all the information that is needed from that, you are able basically to calculate an online map and replace these pre-calculated maps, HD maps, by your online perceptions. And here's a few data from our cars, and that's what we are doing in our cars, interpreting basically the vision data and performing semantic segmentation, so-called, on the images and projecting that onto LiDAR data. We're also having approaches for basically doing this with like pose estimation for vehicles, where you basically calculate bounding boxes of vehicles and then also get like bounding volumes in order to figure out in which directions these cars are moving. And this is kind of here a visualization of one of our more recent publications. The key advantage that we see at TRI that will actually allow us to reach that is that what we call the so-called data advantage that comes from the fact that we are connected to a company, Toyota, that has millions of cars on the road. So the idea there is, or the strategy basically is, that we will leverage in the future those cars to collect data that allow us to become more robust and level to the scale of hundreds of millions of cars instead of just a few hundred like our competitors, for example. By utilizing these cars and these fleets of cars and what they do in the real world, we expect that we are going to be able to accelerate faster than other companies currently. And this is depicted in this figure over here. So like if you look at these so-called older algorithms, let's call them standard machine learning algorithms, like the newer technology, like deep learning methods which scale with the amount of data are great, but they have this problem that labeling this data is enormously expensive. So these companies spend a huge amount of money for labeling data. And that doesn't really scale, and it's probably also too expensive. The only way to get around this is to go to a semi-supervised fashion, which allows you to not, or it frees you from the need of labeling data. And that works on the Toyota level simply if we actually utilize the sensors that we do have in the car, and our plan is in the future to actually have more or utilize these sensors in the car for driver assistance systems to make it more effective. And with such, and here's one example for like semi-supervised or self-supervised approaches that we have developed in the past, which is so-called super depth, which is an approach to basically infer depth from monocular images. And just to give you an intuition how like supervised learning typically works, you have raw data, you have your model, this model generates predictions that, and from that you calculate a loss, and basically based on labels or like ground truth that you provide the system with via labeled data. So like the data is easy to acquire, but labeling the data is super expensive. In a self-supervised setting, you actually want to get rid of this and use the raw data itself to calculate that loss. And I'm going to describe that, how this works like in this kind of a context of monocular depth estimation. So you want to have a single camera that allows you to figure out how far things are away in the world, which is super important when you want to do something like collision avoidance, but also localization, for example. It's basically, localization is easy when you have depth information. And the original work that we have been doing is using stereo camera system. And what your model then basically does is, well, let me go one ahead, and I'm going to be done in a few seconds. You basically take the very same approach, and you perform a view synthesis in which you basically learn how that the left image, or in that case, the right image would look like given your left image. And then you can calculate the loss given you have the true right image from the stereo camera system. But we all know that you can replace the second camera if you take into account the actual movements of the vehicle, and then you can do this also with a single monocular camera. That, of course, you need to have a loss function. Again, some math is also in deep networks. It's not only scripting, but you also need to understand the underlying equations there. And given that, you can actually calculate depth, which is in the lower half of these images, from a monocular image. And here's a video that actually shows that in action. So basically on the top, you see a virtual LiDAR scan. Some people tend to call this VIDAR because it's a vision-based depth projection, simply based on a monocular camera. And we see this as one of the futures of self-driving cars, simply because it frees us from the use of expensive LiDAR sensors, and has a substantial potential for actually like getting or utilizing all the data that human-driven cars can collect in the near future. So coming to an end, what I wanted to tell you is that we are actually working at TRI on improving safety of people and making the world a better place. That's what like all people do in the Silicon Valley. And we have two strategies for doing so, working on chauffeur applications, self-driving cars, and also the Guardian, which is an advanced driver assistance system that makes cars uncrashable, so to say. And the technology that we're using is probabilistic reasoning and machine learning. Thank you.